everybody, and welcome to another episode of Echo Live. My name is Anna from the Michigan Science Center's Echo Distance Learning Program, and today we're going to be talking about what I like to call surprising circuits. So we are going to be talking all about circuits today, but let's start with the most basic form. I see that we've got lots of friends starting to join in through our various platforms here. So welcome everybody on YouTube, welcome all of our friends on Facebook, and of course, welcome to our friends joining in through Zoom. If you haven't done so already, go ahead, introduce yourself in the chat or the comments feature where you're watching. Make sure that you know I can see you and hear you, and that way I know that you can see and hear me okay as well. You can ask questions about any of our various demonstrations or experiments that I'm going to show you throughout our program today. And you can also answer some of the questions that I have for you as well. So we are going to start talking about circuits. And we said we want to start by keeping it very, very simple. So we're all probably familiar with circuits. We use them all the time. Now, next thing you can tell me in the chat after you've introduced yourself is, can you name me an example of something that you've used today, maybe a device or a piece of equipment that uses a circuit? So if you are familiar with things that might utilize a circuit, give me an example of something you have personally used today. I'm sure that we've all used at least one thing that relies on a circuit in order to function. Let's see. So Justin in Zoom has a great answer. Justin says they use their toothbrush, probably an electric toothbrush then, I'm guessing, either one that has a battery inside it or maybe even a rechargeable battery that you charge it on a stand. That's a great example of something that uses a circuit, but I bet that's not the only thing that you've used powered by a circuit today. If you have anything else in mind, you could go ahead and you can tell me that in the chat as well. Lots of people naming great examples, turning on the lights in your house. So I know that I turned on the lights when I woke up this morning. Theo says the computer has all sorts of circuits inside it, not just one, right? That's a great example. Lights, computers, iPhones, right? Phones rely on circuits as well. Lights, let's see. Good answers, everybody. So we are pretty familiar with circuits, or at least we know a lot of examples of things that rely on circuits in order to function. Great answers, everybody. Vanita tells me her computer as well. All right, so we're going to go through the very, very basic parts of a simple electrical circuit. So a circuit that is carrying electricity. Oh, I have to name one more example here. Aaron says that his Little Bits R2-D2 robot model uses circuits. All variations of R2-D2 run on circuits, even the real one, I'm sure. All right, so let's talk about those basic parts of a circuit here. We have a diagram of what we call a simple electrical circuit. Now, these are the four things that you have to have in order to have a circuit. There are other things you could add to this diagram, but that might make it a bit more complicated. In its most basic form, right, a circuit is something that allows the flow of electricity through it in order to accomplish a task or to power up a device. In order for that to happen, right, we have to have a power source. Now, in this diagram, the power source is the battery. So not all circuits rely on batteries, right? So if you named your computer or your lights, right, those are powered by the electricity in our walls, which comes to our house through wires. So that's an even larger circuit, right? But definitely not a simple circuit. But the power source can come from anything that is going to provide the electricity to your circuit. In this case, it is a battery. That battery is going to create a difference in charge between its two poles and allow the flow of electrons through the circuit. They also need, right, something to travel through. So in this case, we have wire. So wire is the path that the electrons are following through this circuit. So it needs some sort of conductor, some sort of medium or object to travel through. In this case, it would be the wire. Now, if you think about your lights, right, or really even most of our devices, they also have what we call a switch, something that starts and stops that flow of electricity. That allows us to create what we call either an open or a closed circuit? Tell me in the chat if you remember from what we've discussed on Echo Live in the past, or maybe you know this from your own prior knowledge, which type of circuit allows the flow of electricity? Is it an open circuit or is it a closed circuit? Which one would allow the electricity to flow? Open circuit or closed circuit? Tell me in the chat. This is definitely something we've talked about before. I'll give you a moment to think about it. Think about those two words. Is it an open circuit or a closed circuit that allows electricity to flow around it? All right, some answers starting to come in. We've got some answers for open and some answers for closed. So let's think about this question together, right? If we think about maybe even using our hands to replicate either an open circuit or a closed circuit. So if you're not holding your iPhone to watch this show, go ahead and try this with me. Give me an open circuit. So put maybe your thumbs together, but keep your other fingers open. If this were the wire in our circuit, right? If this were our wire and we had all those other components hooked together, would this allow for the flow of electricity to power up our device? Open circuit? No, right? We need the circuit to be closed, right? When the circuit is closed, our wire and our switch and our load, and we'll get to that one in a moment, and our battery or our power source are all connected. When you open a circuit, you stop the flow of electricity, which is a good thing, right? We don't want our lights to be on all the time. We want the ability to either open our circuit when we want to turn things off, but close our circuits when we want to turn our devices on. So in a simple circuit, right, a switch would be an easy way to allow us to open or close the circuit. The light switches in your house work exactly the same way. When you flip a light switch on, it actually closes your circuit. It connects your circuit all together, and that allows the flow of electricity from your walls through your light bulbs and back, and then you get a light, right? But when you want to turn your lights off, right, you flick the switch the other way and it breaks open the circuit. So a really easy way to think about that, right? That if you want flow, you need a circle or a closed circuit. And if you want to stop the flow, all you need to do is open the circuit. And that's what a switch allows us to do. Now, switches don't have to be light switches, right? It could be you either plugging in or taking something out. In that case, you would be the switch in that circuit. It could be a button on your phone that either starts or stops that flow of electricity. That would be the switch. Now, the last part of that diagram was what we would call the electrical load. The electrical load is actually the device that you are trying to power. So we have the battery, the source of the power. We have the conductor, which is the wire. We have a switch, which allows the start and stop of electrical flow. And then in this case, right, our electrical load would be a light bulb. But switches don't just control light bulbs, right? They can control your stereo, your cell phone, your toothbrush, right? So, but these are the 4 very basic pieces of a simple electrical circuit. Now let's take a look at a simple electrical circuit, which I've constructed right here on my table. So like we said, you only need those 4 basic parts. You don't have to have any sort of electrical degree in order to construct a circuit. So in this case, right, I used a battery, just like in that diagram, right, because it's not very safe to play with the electricity that comes out of your walls. But these batteries, generally this DC current and the amount of voltage that this produces is not dangerous. So what I've done is I've just taped 2 D cell batteries together to be our power source. Then we have alligator clips or wires. So just like in that diagram, we have wire that's going to carry the electricity to my device here. And what I've done is I've actually created a switch just using some very simple materials like these paper clips. So when we attach, we'll leave our circuit open for right now. So you can see I've pulled our paper clip away from the light bulb lead. So the light bulb is on top. I've pulled my paper clip away from it. So even when I connect our alligator clips here, so even when I connect them, we still don't have flow of electricity because our circuit just like we talked about in our house, is open. There's a gap here, so the electricity doesn't have a place to flow. So in this case, like we said, a switch can be very simple. All we need to do is turn our paper clip, right? That acts as our switch, and you can see that we get our light bulb to glow very, very bright. Now, this is an LED, which is why it doesn't appear very bright when I point it this way, but because of the direction of the bulb inside, when I point it right towards you, there's this really, really bright light that comes off of our little, very simple electrical circuit. Now, you don't have to use D-cell batteries, right? You only need about 1 to 1.5 volts of power to light up a little LED bulb like this. So you could even take something like a little coin cell or watch battery and create yourself a really simple little pocket flashlight just to test out your own circuitry skills. Let's go ahead and make sure we close that circuit one more time. We'll pull it off here because we're going to use our battery pack, our power source, for a couple other examples of circuits here today. But before we do that, we want to talk about what types of things you could include in a circuit if you were interested in building one at home. We need to know what kinds of things make good conductors or good wires for our various circuits. Now, you don't have to use wire, but we definitely need to test what we call the conductivity of different objects if you're considering them to be part of your own circuit. Go ahead and scoot a couple things out of the way. And then I've got a tray of what seems to be some pretty random stuff here on the tray. So I've got a hot dog bun, a little orange or a clementine, some Play-Doh, a pipe cleaner, a popsicle stick, glass of water, some electrical tape, and a pair of wire cutters. All right, now of those objects I named, I know I went pretty fast, but I'll give you a zoomed in look here. Of those objects I named, which ones do you think make good conductors? Good conductors. Go ahead and tell me in the chat what would be an example of a good conductor. And then we're going to test it out using our handy dandy voltmeter. Now, we've used the voltmeter on past episodes of Echo Live to check how much power is coming out of something like a battery or a different type of electrical device. If we were to put the two ends of our voltmeter here, if we were to put it on voltage, and take our two leads here and connect it to our battery pack, we'd get a reading on voltage. So you can see that I hold it nice and still, make sure it's not moving. Not very good at doing that. It seems to fluctuate. Let's see. We don't want to go to millivolts. We want to get a nice good reading. But we are getting about 1.5 to 2 volts of power, and then it kind of trails off there. So we don't just measure voltage with a voltmeter, despite its name. We can also measure this little symbol right here. Let me see if I can zoom in well enough for you to see it. This little symbol right here, that is the symbol for ohms. Everyone say it with me. Ohms. Now, I don't mean like in yoga, that kind of ohm, but this kind of ohm measures what we call resistance, or the pushback on the flow of electricity through a circuit. So let's see what you guys thought. What did you think? Which one would make a good conductor? A couple people voting for, let me scroll all the way to the top of my question here. We've got lots of votes for the orange. All right, lots of votes for the orange. A couple people saying the electrical tape. So that makes sense, right? If we use it for electrical purposes, right? Maybe that's why we call it electrical tape. A couple people know that maybe the water might be conductive, the pipe cleaner, the orange, the pipe cleaner, the tape. All right, so we've got some really great answers here. Let's put them to the test. So we're going to test the conductivity of our various objects using our voltmeter. And we said we're measuring this in ohms, but we said that ohms measures resistance. So what we want is a low reading of resistance for something that is a good conductor. If that doesn't make sense quite yet, let me share one more picture with you. Now in this picture, we can see that resistance is symbolized as that hand pushing back on those electrons. So the electrons are trying to flow through the circuit in the direction of our current. So those blue arrows represent the flow of our electrons through a circuit or through a wire or another conductor, but resistance is pushing it back. If you have a lot of resistance, that means you're not a very good conductor. And if you have a high number or a high reading for resistance, that's not so great, right? Because a high resistance means there's a lot of pushback, so the electricity doesn't flow very easily. But if you have a low reading on resistance, that means that you are probably a pretty good conductor because you're not pushing back, you're actually allowing the electricity to flow. Now, a lot of people told me the orange. That was our first guess. So let's go ahead and try the orange first. Let's go ahead and poke our probes here, our little electrodes, into our orange and see what kind of reading we get. All right, so if you read it right on there, we are at about, we're over 300, over 400 now, ohms. Huh, that's a pretty high resistance written on there. And so although there is a flow of electricity, the resistance is actually pretty high through our orange there. Now, a lot of people also telling us the water. Let's go ahead and check the water. Let me make sure you can see. Place it in the center. We'll put one probe on each side and get a reading on our water. Now you can see that the resistance of our water is actually very, very low. It's under 1 on this reading that we're getting here. So the resistance in this water is very, very low. So that helps to explain, right, why water should always be kept away from our electrical devices, or that we should never be sitting in water or near water when there's an electrical storm outside, right? Because water can help to conduct electricity to or from your body, which can cause you a lot of harm. And it can also damage a lot of your electrical devices because the flow of electricity through water can be really, really unpredictable. Now, if this was pure water, it would actually be very, very different. If this was just water with nothing else in it whatsoever, water is actually a good insulator. It's not very good for electrical flow, but that's extremely rare. Water has this very special property that we've talked about lots of times on Echo Live, that it is polar. Those molecules love to rearrange themselves, love to form bonds with other objects and other charged things, which makes it a great conductor. So if there's anything in this water whatsoever, even the minerals from your tap, which is where I got this water from, that immediately makes the water a conductor, and a really, really good one at that. Now, some people telling us they think the electrical tape would make a great conductor. So let's go ahead and give that a reading next. So we've got our 2 probes here. Let's go ahead and test our electrical tape. And what do you notice? We're actually not getting any reading whatsoever from our voltmeter here, which is telling us the resistance. That means that the resistance is actually so high in this electrical tape that the probes can't actually detect any flow of electricity. So nothing whatsoever. So if you guessed the electrical tape, right, that was a good thought. You know that we use it in electrical applications, right? So maybe you've used some electrical tape at home if you've been doing repairs, or you've seen someone else use it, maybe on your robotics projects, all that kind of stuff. But electrical tape is actually good for those purposes because it's not a conductor. It has a really, really high heat resistance, so it's not going to melt, but it's also not a conductor, and so it's not going to carry your electricity across your circuit or across any of your electrical devices that you might be working with. So good thought, but this is actually not conductive, or very, very low. Such a low conductance that we actually can't even measure it here with our voltmeter. Now I'd like to try some of the less guessed and less expected ones. So now nobody told me that the hot dog bun, or here, that our hot dog bun was going to be a conductor. So we know that this is made of bread. So let's go ahead and get a reading, if we can, on our hot dog bun. Let's go ahead and check that one out. But would you look at that? Take a look at our reading there on our voltmeter. It's actually getting a reading off this. Now, it's a pretty high resistance, right? Over 300 is a pretty large resistance to electrical flow. So while you might not want to use hot dog buns in your wires in your home or to power up your lights, it actually does carry electricity, right? So we have to think about what bread is made out of. Bread is mainly made out of flour, right? But there's all sorts of other ingredients in it as well. There's also water in here, which we said makes a great conductor when it's combined with other things. And there's also salt inside white bread as well. So while it's not a very good conductor, it is a surprising example of a conductor. So bread, conductive. All right, let's check out some other ones here now. A couple of people guessed that the pipe cleaner would be a good conductor. So let's go ahead and check that one out. Now, the trick with a pipe cleaner, right, is that it's wrapped in this really fuzzy coating. And so if we hold it only on there gently, we just touch our two probes here, we don't get a reading, right, because the furry coating or that fabric material that's kind of intertwined into it is not conductive. So it's not conductive, and so we don't get a reading. But if I push on the pipe cleaner pretty hard and we get down to that metal coating on the inside, you can see that the metal coating on the inside is a good conductor. So we actually do get a reading down there on there. I'm trying not to touch my skin onto it, but try just to touch the metal. And we do get a reading off of it, which is pretty cool. So the pipe cleaner, you were right, is conductive. A little bit difficult to get through that fuzzy protective layer, but that works really similarly, right, to even the wires that are on my voltmeter here. Inside, there's a conductor, but on the outside, we've protected it or insulated with rubber, which is not very conductive, which keeps our electricity safe and flowing as it should. Now, how about the Play-Doh? No one guessed the Play-Doh that I saw. No one really thought about the Play-Doh as being a good conductor. Maybe we're not sure either way, but let's go ahead and give that one a look. Let's put our two probes in. And our reading, right, is relatively low. We fluctuate, right, just like with any of them, as our electricity finds a path between or across our conductor. But we're just a little bit over 1 here on our scale, which is a pretty low resistance, which means that this Play-Doh is actually a really, really good conductor. Now, I have a recipe here for this dough. So any sort of Play-Doh that you purchase from the store would probably act as a good conductor. And so you can actually use it if you're considering any of our projects that I'm going to show you. You can actually consider using Play-Doh as a wire or a conductor for your circuit. You can build your own switches out of it, but it only works when it is kind of damp. So let me show you the recipe that I used because I actually didn't have any Play-Doh at my house. Instead, I made my own following this recipe. Now, in this recipe, I combined flour, water, salt, lemon juice, and vegetable oil with a little bit of food coloring. And then I mixed that all together, heated it over the stove just to form it into a dough, just like you would with dough that you were turning into bread or cookies, anything like that. So I mixed it on the stove. But tell me, based on what you think you know about chemistry, or about what we've talked about so far, what ingredients on this list are what make this dough conductive? Which of the ingredients are important to turn this dough into a good conductor? Tell me what you think in the chat. Flour, water, salt, lemon juice, vegetable oil, and food coloring. Which of those ingredients would make this dough conductive? What ingredients in the dough make it conductive? Let's see, we've got some answers starting to come in. Yeah, so you know that it's more than just one of these, right? Of course, water is one of those things. We said that water on its own, not super conductive, but if you combine it with other minerals or ingredients, right, water becomes a great conductor of electricity. So water. Salt is another one of those ingredients that makes it conductive. So the salt is what we call an electrolyte. Electrolytes are actually charged ions, and the salt will very, very easily interact with the water, and it's great for carrying those negatively charged ions through a circuit. And you all got it, the lemon juice as well. Now, you might remember that we actually built a circuit entirely out of lemons on a past episode of Echo Live. We didn't even use a battery. We actually used the lemons as a battery themselves. Lemons are great for these kinds of experiments because they are acidic, which kind of interacts with the other ingredients to form new compounds that are charged, but it is also an example of an electrolyte, just like salt. So if you follow that recipe, and you decide to make your own dough, keep in mind which of those are the important ingredients to make your dough a good conductor. Now, once you've done that, right, you can form your dough into a circuit. So you can roll your own wires. So if we roll it into kind of little circuits, you could make a shape on the table. Go ahead and we'll try to quickly construct one here. Dun, 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 dun. All right, now the dough does not provide all the pieces of our circuit, right? We said that this is acting as our conductor or as our wire. We're missing, right? We're missing an electrical load, right? So we've got another little LED light bulb here. We're missing an electrical load. So we'll go ahead and we will attach our two wires with to our little LED light bulb there. And then of course, we need a power source, which is going to come from our battery pack, which we used earlier. So let's go ahead and we'll try powering up our circuit. Now, if you try this at home and it doesn't work on your first try, the first thing I would suggest is reversing the polarity of your circuit. And what I mean by that is just turn your battery pack around and try the other sides of your leads. And there we go. If I point my bulb towards you a little further, our light begins to light up. That's because batteries are direct current, that electrons flow in only one direction. And so you can't have them switched. Otherwise, your power doesn't flow through the LED appropriately and it won't work. But really, really simple stuff. Play-Doh makes a great conductor. Now I've got one more experiment to show you using something maybe a little unexpected, but something we've mentioned so far that you can use to create your own circuit. And that's actually just using salt. And we can create kind of a fun craft or activity on creating a rainbow salt circuit. Now, while I get this one set up, if you have any questions about the activities that we've done so far or questions about electricity, go ahead and tell me in the chat. I know it's good to give you guys a moment to think about those. So think about it. Let me know if you have questions. I would love to answer some of them that you might have about our circuit activities or our simple circuits that we've built so far. Someone asked in Zoom, can we do a crystal episode? And the answer is yes. I mentioned this on Friday, I believe, but we are doing crystals this week on Wednesday. So if you are interested in crystals, learning about them, how to make them even, you should tune into Echo Live on Wednesday because we'll be talking about crystals then, because I know that's something that you've all suggested and really wanted us to try. And so I'd love to do that. All right, let's see. No questions in Facebook just yet. Oh, Justin asked, do I know Mark Rober? No, I don't. Man, do I wish I do. Do I wish that I did? He is so cool and his YouTube channel is amazing. He does a really great job. If you don't follow Mark Rober on YouTube, you should check out his page because it is super, super cool. One day I want to be just like him. So very cool. All right, so let's go ahead and keep sending your questions if you have them, but let's take a look at our last simple circuit we're going to create. Now, inside this little squeezy bottle here, I just have some white glue, and this is just what we call a dropper bottle. And so I've just put some white glue in there so that I can really easily draw with my white glue here on our page. Now, the object, we don't want to tilt my bottle up. We just want to draw something where it would be easy for us to connect all of those circuit components that we've discussed so far today. So maybe something kind of swirly and zigzaggy, right? This glue is going to act as a path. You can see that I've got one wire down, but we'll need another one because we have both a positive and a negative end of our battery pack, right? So we need two places to attach into this circuit. And you, if you try this at home, can make this however you'd like it to look. So I've created two wires here, but glue is not very conductive. We can even test that with our voltmeter that we use to test the conductivity or the resistance of our other objects so far. And even though glue is wet and there is a small amount of resistance, we're measuring, or I'm sorry, there's a large amount of resistance and there's a little bit of conductivity. We're still measuring a pretty high number. It was a little over 20. And so what we're going to add next is that same salt that we've talked about for our conductive dough. Now, I colored this salt with a little bit of food coloring, just because I think everything's more fun when it's colorful. So we've got blue on one side. We're just sprinkling that right across our glue line there. And it's giving that salt, that electrolyte, a path to flow through. All right, so now that we've covered our circuit here, the fun part is picking it up, and you get to do a reveal. So if we just shoop, they look like gummy worms, but remember that they are not gummy worms, and so they probably wouldn't taste very good if you were to eat these. So we've got our 2 gummy worm circuits here, and then we're just going to use a couple more things. We need to attach our battery pack, but we also need our electrical load. So we're going to attach our electrical load just by poking the 2 ends of our LED into the glue, make sure that they have good contact with the salt. We can attach our paper clips here. You could even put your wires right into the, want to switch the other way, right into the glue. But this will keep my alligator clips nice and clean. And so I can use them again for something else. All right, so we've got 1 in and 2 in. And remember, I always forget to check the direction of my LED. So if it doesn't turn on right away, you know what we need to do. We're gonna have to switch the direction, or we're gonna have to switch the direction of our battery pack. That way we have the negative end of the battery going to the negative end of the LED, and the positive end of our battery going to the positive end of the LED. Here we go, here we go. All right. Try one more light bulb here. You always come with a spare, just in case. Oh, there's my spare. All right, try our light bulb that way. If it doesn't work, switch it around. Uh-oh. Got to make sure you have good contact, right? And if you don't, let's give it a quick check with our voltmeter here. Let's make sure that we have electricity flowing through our circuit. It says we do not, which means that we probably have a break somewhere inside. Go ahead and scoot our paper clips up just a little bit higher. Make sure that everything has good contact. Looks like we might have a break in our salt, actually, if we're. All right. Go ahead and give this a try. And it would go like this, right? That my very last activity, which is, of course, my favorite one, is not working as well as I might want it to. Try one more thing. Make sure our circuit is not connected in the center. And alas, now what we can check is it's possible that we have a bad light bulb, and we would know that if we connect. Nope, it's not our light bulb. It is a problem with my circuit. So problem with my circuit probably can be addressed. Let's see if we have any final questions, and I can tinker with this a little bit more. And of course, you can find these activities on the Michigan Science Center's website. So if you are looking for activities that you can try, someone's giving me lots of encouragement, and I appreciate it. It looks like we have a break somewhere in our glue. I'm trying to find it, and I actually don't see one, but it could just need to have a little bit more salt added to our circuit here. Jennifer asked a great question, which is, why is electricity so dangerous? That's something that we're all pretty familiar with, right? Is that electricity can be really, really dangerous. And that's a lot to do with the amount of electricity we have inside our body that's keeping us alive. So your heart runs on what we call pacemaker cells. Pacemaker cells are cells in your heart that actually fire little electrical signals that tell your blood to pump, or tell your heart to squeeze to pump your blood. If you were to be electrocuted and that electricity passed through your heart, it could short circuit those pacemaker cells. So that's one of the biggest dangers when it comes to electricity. But of course, we know that electricity can be very, very hot as well. So there's always signs around really dangerous electrical equipment that tells us, you know, danger, stay away from these things, because if they were to spark, right, they could burn you very, very badly. So there's all sorts of reasons that electricity is dangerous, but the most important one, right, is that we want to keep the electricity inside our body separate from the electricity outside our body. We don't want to connect those circuits unless a medical doctor has something, or they're trying to solve a problem for you using an electrical device. So Kelly asked a great question. If a circuit is open, will the electricity flow? The answer is no, right? Electricity can't flow through an open circuit. It only flows through a closed circuit when it has a conductor to travel through. Now, some electricity is so powerful, and it can actually travel through the air. The air, if it has enough humidity, can act as a conductor. So that's not to say that electricity is always safe inside wires. Sometimes it's dangerous to even be near something that has electricity in it, because air can be a conductor as well, because it has water in it, right? And we said water is a great example of a conductor. A couple people saying that they have been shocked by electricity before. Thankfully, you are still here to watch this program, so I'm very, very glad that you weren't seriously injured by that shock, and hopefully now we know just how dangerous some of that electricity can be. I've also been shocked. Thankfully, nothing too severe, nothing that's ever caused me very, very bad damage. But now I have a very, very healthy respect for electricity, because I know that it can be harmful and very, very painful. Let's see. If we have no last questions, here's what I'm going to do. I'm going to get my circuit working, and I will post a photo of it working in the comments of this video. Of course, if you're looking for activities that you can try, check out the Michigan Science Center's website. These programs are free, and we love to show you activities that you can do at home, but you can find these recipes, find these activity guides on the Michigan Science Center's website, listed right here on the bottom, mi-sci.org/@home-science. And we hope that we will see you back here tomorrow for even more Echo Live. We've got a really fun program planned for you, and so I hope you guys all have a great rest of your day, and I will see you back here tomorrow. See you later.